The James Webb Space Telescope just scanned the nucleus of 3I Atlas, and the signal coming back is not what scientists expected. What it revealed suggests this object may not behave like any comet we have ever studied. About 40 billion kilometers away, drifting through the dark outskirts of our solar system, a silent traveler is moving past the planets. At first, it looked like just another icy comet. Astronomers see new comets every year, but the deeper scientists looked into this one, the stranger the data became. When the discovery was first announced through the Minor Planet Center, observatories around the world began tracking the object immediately. Within days, instruments from Hawaii to Chile were collecting measurements. Orbital calculations at NASA's Jet Propulsion Laboratory confirmed something astonishing. This object did not come from our solar system. Its speed, direction, and energy all pointed to the same conclusion. It had entered from interstellar space. That alone made it extremely rare. Before 2017, scientists had never confirmed a visitor from another star system passing through our cosmic neighborhood. Then came Oumuamua, discovered by the Pan-STARRS telescope in Hawaii. 2 years later, another traveler appeared, Comet Borisov. Now, astronomers believe this object, now cataloged as 3I, Atlas, may be the third confirmed interstellar visitor ever detected. But what the James Webb Space Telescope just saw when it scanned the nucleus is what truly caught the attention of scientists. Because the data hints that the object might not behave like a normal comet at all. And that is where this story begins. To understand why scientists are paying such close attention to 3I Atlas, it helps to understand where objects like this come from. Our solar system formed about 4.5 billion years ago. During that time, planets were still growing from clouds of dust and gas swirling around the young sunday. Huge numbers of leftover fragments remained after the planets formed. Many of those fragments were icy bodies that became comets. Some were thrown far away by the gravity of the giant planets. Many of them now live in distant regions like the Kuiper Belt and the enormous spherical cloud that surrounds our solar system, known as the Oort cloud. The Oort cloud may stretch nearly a light year from the sun and could contain trillions of icy objects. But not all of those objects stay here forever. During the violent early years of planetary formation, giant planets like Jupiter can fling smaller bodies completely out of their home star systems. When that happens, those objects begin wandering the galaxy. For millions or even billions of years, they drift through interstellar space. Most will never encounter another star system again, but occasionally one passes close enough to another star to be pulled inside. That is likely what happened with 3I Atlas. When astronomers first spotted it using the Atlas survey telescopes, they noticed its speed immediately. The object was moving too fast to be bound by the sun's gravity. Calculations performed by orbital specialists at NASA's Jet Propulsion Laboratory confirmed the trajectory. 3I Atlas came from beyond our solar system. Its path through space is hyperbolic, meaning it will not stay here long. It will pass through the solar system once and then continue back into interstellar space forever. This type of orbit is extremely important to astronomers because it confirms the object is not native to our system. That alone makes every piece of data valuable, because objects like this carry information about distant star systems that we may never visit. They are physical samples of other planetary systems drifting through space. As soon as the discovery was confirmed, observatories around the world began studying the object intensely. The Keck Observatory in Hawaii pointed its powerful mirrors toward the faint moving target. The European Southern Observatory in Chile used the Very Large Telescope to capture spectral measurements of the object's light. Even older observational archives were checked. Astronomers searched through previous sky surveys to see if the object had been accidentally photographed before its official discovery. Meanwhile, scientists working with the Harvard Smithsonian Center for Astrophysics began analyzing the object's brightness and rotation. Brightness changes can reveal how an object spins and what shape it might have. But the most important observations came from space. The James Webb Space Telescope. Webb was designed to observe the universe in infrared light. This allows it to detect heat signatures from extremely distant objects. Even bodies far beyond the orbit of Jupiter can produce measurable infrared signals. When Webb's instruments focused on 3I Atlas, scientists hoped to learn something simple. Was it made mostly of ice, like a comet, or was it rocky, like an asteroid? The results surprised them. Instead of showing clear signs of water vapor or gas escaping from the surface, the readings suggested something different. The nucleus appeared unusually dark. Even stranger, its surface seemed to absorb far more light than typical comet material. That raised immediate questions. Normal comets usually release gas when they approach the sunday. As sunlight warms the icy surface, frozen gases begin to evaporate, creating the glowing coma and tail that make comets so beautiful in the night sky. But early data from the James Webb observations suggested that 3I Atlas might not be releasing much gas at all. If that is true, the surface could be covered by a thick crust formed during its long journey between the stars. When objects travel through interstellar space for millions of years, they are bombarded by cosmic radiation. Over time, this radiation alters the chemistry of their outer layers. Simple molecules break apart and recombine into complex organic compounds. Scientists call these radiation process materials tholins. Tholins are extremely dark and absorb large amounts of light. Similar materials have been observed on distant objects like Pluto and certain Kuiper Belt bodies. Laboratory experiments on Earth have shown that tholins can form when ice mixtures containing methane, nitrogen, and water are exposed to radiation in extremely cold conditions. If the surface of 3I Atlas contains such compounds, it would explain the dark infrared signature detected by the James Webb Space Telescope. But the mystery does not stop there. Because when astronomers analyzed the object's rotation, they noticed something else. The brightness variations suggest the nucleus might not be round. It may have an elongated or irregular structure. That discovery immediately reminded researchers of Oumuamua, the first interstellar object detected in 2017. When scientists studied Oumuamua using data from the Hubble Space Telescope and ground-based observatories, they discovered that its brightness changed dramatically as it rotated. That suggested the object might be shaped like a long cigar or possibly a flattened disk. Such unusual geometry sparked intense debate among astronomers. Some researchers proposed that tidal forces from a close encounter with a star might have stretched the object. Others suggested it might be a fragment from a larger planetary body. Now, 3I Atlas may provide another example of how strange interstellar debris can be. But this time, astronomers have better tools. In 2021, the James Webb Space Telescope launched with instruments far more sensitive than anything available during the discovery of Oumuamua. Webb can analyze faint heat signatures and detect chemical fingerprints in light coming from distant objects. That means scientists can study the composition of 3I Atlas in ways that were impossible just a few years ago. And the next series of observations could reveal even more. Because astronomers have already scheduled additional observation campaigns using Webb, Keck, and the European Southern Observatory's telescopes over the coming months, each new observation adds another piece to the puzzle. And with every new piece, the mystery surrounding the nucleus of 3I Atlas becomes deeper. Because what the James Webb Space Telescope has already seen suggests that this object may be carrying secrets from another star system. Secrets that have been traveling through the galaxy for millions of years before finally arriving here. The moment astronomers realized the James Webb Space Telescope could track the thermal signature of the 3I Atlas nucleus, the investigation entered a completely new phase. Until recently, interstellar objects were observed for only a short window of time before they disappeared back into deep space. Oumuamua, for example, was already leaving the solar system when scientists realized how unusual it was. By the time the world's most powerful telescopes focused on it, the object was already fading into darkness. But 3I Atlas appeared at a time when astronomy had changed. Today, global telescope networks work together almost instantly when something unusual appears in the sky. Automated surveys scan the heavens every single night. Projects like ATLAS, Pan-STARRS, and other deep sky surveys capture enormous volumes of data. When a new object moves against the background stars, computers flag it immediately. That is exactly how 3I Atlas was discovered. The ATLAS survey system, originally built to detect potentially hazardous asteroids, noticed a faint object moving across multiple frames of the night sky. Within hours, the discovery alert spread across astronomical networks. Observatories around the world began confirming the detection. The Minor Planet Center cataloged the object. Then came the calculations. Orbital specialists at NASA's Jet Propulsion Laboratory began analyzing the trajectory using fresh measurements from multiple observatories. Within a very short time, they reached the same conclusion that stunned scientists during the discovery of Oumuamua. The object was not gravitationally bound to the Sunday. Its speed exceeded the escape velocity of the solar system. That meant one thing. This was another interstellar visitor. Immediately, the object received the designation 3I Atlas, marking it as the third confirmed interstellar object detected passing through our solar system. But the real surprise came when astronomers began measuring its brightness. At first glance, the object looked faint and ordinary. But brightness curves gathered by observatories, including the Keck Observatory in Hawaii and the European Southern Observatory, began revealing subtle variations. These variations suggested the object might be rotating slowly. Rotation tells scientists a lot about the structure of a comet or asteroid. If an object spins irregularly, it may have an uneven shape or surface features that reflect light differently. When astronomers plotted the light curves of 3I Atlas, the pattern did not perfectly match typical comet behavior. This immediately triggered deeper investigation. Researchers from the Harvard Smithsonian Center for Astrophysics joined the analysis, comparing the object's brightness fluctuations to those of other known comet nuclei. They also looked at previous data collected from objects in the Kuiper Belt and distant asteroids. But 3I Atlas still stood out. At that point, scientists realized something important. If they wanted to understand the object's surface composition, they would need infrared observations. That meant one telescope above all others, the James Webb Space Telescope. Webb was designed to detect extremely faint infrared signals from distant galaxies, newborn stars, and planetary atmospheres. But it is also perfect for studying cold objects in the outer solar system. Even small bodies, drifting billions of kilometers away, can produce detectable heat signatures. So astronomers scheduled observation time. When Webb's instruments turned toward 3I Atlas, researchers hoped to detect familiar cometary gases like water vapor, carbon dioxide, or methane escaping from the nucleus. But the first datasets suggested something unexpected. The nucleus was not behaving like an active comet. Instead of showing strong thermal emissions caused by gas escaping from the surface, the object appeared colder than predicted in several areas. This could mean the surface has been hardened over time. Interstellar objects spend enormous periods traveling between stars. During that time, they are exposed to cosmic radiation from supernova remnants, stellar winds, and high-energy particles traveling through the galaxy. Over millions of years, this radiation slowly transforms the chemistry of exposed ice and dust. Scientists have reproduced this process in laboratory simulations. When simple molecules like methane and nitrogen ice are bombarded by radiation, they can form complex organic residues known as tholins. These substances are extremely dark and absorb most of the light that hits them. They also act like a protective crust. If 3I Atlas developed such a crust during its interstellar journey, it could prevent volatile gases from escaping easily when the object enters a new star system. That would explain why the object appears less active than expected. But there was another possibility scientists began discussing quietly. Some researchers wondered if the object might contain more rock than ice. If 3I Atlas formed in the inner region of its original star system before being ejected into interstellar space, it could contain a mixture of rock, metal, and frozen compounds. That type of structure could produce unusual thermal patterns in infrared observations. To investigate further, astronomers began analyzing spectral fingerprints within the infrared light captured by Webb. Spectroscopy allows scientists to identify molecules based on how they absorb or emit light at specific wavelengths. This technique has been used for decades by telescopes like the Hubble Space Telescope and ground-based facilities such as the Keck Observatory. But Webb's instruments are far more sensitive. Even extremely faint molecular traces can appear in its data. Early spectral analysis suggested the presence of carbon-rich compounds on the surface of the nucleus. However, researchers are still cautious about interpreting the results. Spectral signals can be complex. Multiple materials can produce overlapping features in infrared wavelengths. That is why scientists are planning additional observation campaigns. Upcoming observation windows in late 2026 and early 2027 could provide clearer spectral signatures as the object's viewing angle improves. These future observation events are already generating excitement within the astronomy community. If Webb confirms complex organic materials on the surface of 3I Atlas, it could reveal new information about how planetary systems form across the galaxy. Because interstellar objects are essentially cosmic messengers. They carry physical samples from distant star systems. Studying them is like examining fragments of another solar system without leaving our own. That is why every new measurement matters. Every spectrum, every brightness curve, every thermal reading, all of it helps scientists piece together the story of where this object came from and how it survived its long journey through the Milky Way. And as more telescopes join the investigation, one thing is becoming increasingly clear. 3I Atlas may be one of the most scientifically valuable interstellar visitors ever detected. Because unlike previous objects that slipped away quickly, this one arrived at a time when our observational technology has reached a completely new level. And the deeper scientists look into its mysterious nucleus, the more questions begin to appear. Questions that the next round of observations may finally begin to answer. As the investigation moved forward, the timeline of observations began to matter just as much as the object itself. Astronomers realized that the coming months and years could become one of the most important observation windows for interstellar science in decades. When an object like 3I Atlas enters the solar system, its position relative to Earth constantly changes. Sometimes it is hidden behind the sun's glare, making observations difficult. Other times it moves into darker parts of the sky where telescopes can gather much clearer data. According to orbital predictions calculated by specialists at NASA's Jet Propulsion Laboratory, several key observation windows will occur between late 2026 and early 2027. During these periods, the viewing angle between Earth, the Sun, and 3I Atlas will improve dramatically. That means telescopes will be able to capture longer exposures and more detailed measurements. For astronomers, those future dates are critical. The first major observation campaign is expected during the final months of 2026, when the object moves farther from solar glare and becomes easier to track during nighttime observations. Facilities like the European Southern Observatory's Very Large Telescope are already preparing proposals to dedicate observation time specifically to the study of 3I Atlas. These observations will focus on one goal: understanding the true composition of the nucleus. Spectroscopy will again play a central role. By studying how the object absorbs and reflects different wavelengths of light, astronomers can identify the chemical compounds present on the surface. Even extremely faint molecules can leave recognizable fingerprints in spectral data. Researchers at the Harvard Smithsonian Center for Astrophysics are particularly interested in detecting signs of carbon-rich materials. Organic compounds are common in comets, but the radiation environment of interstellar space could create more complex molecules than those normally found in objects formed inside our solar system. If Webb confirms the presence of these materials, it would provide valuable evidence about chemical processes happening in distant planetary systems. But chemistry is only one part of the mystery. Another question scientists want to answer involves the structure of the nucleus itself. Brightness measurements from telescopes like the Keck Observatory already suggest that 3I Atlas may have an irregular shape. If the object rotates slowly enough, astronomers may eventually build a rough, three-dimensional model of its form using changes in reflected light. This technique has been used successfully for several asteroids and comets. As the object spins, different surfaces reflect sunlight toward Earth. By measuring those changes carefully, scientists can estimate how elongated or flattened the object might be. If 3I Atlas turns out to have an unusual geometry similar to Oumuamua, it could provide clues about the violent processes that shaped it long ago. Fragments thrown out of young planetary systems can experience powerful gravitational interactions before escaping into interstellar space. These interactions may stretch, fracture, or reshape objects before they begin their long journey through the galaxy. But the investigation does not stop with optical observations. Thermal data will continue to play a major role. The James Webb Space Telescope will likely attempt additional infrared scans of the nucleus during future observation windows. These scans will help determine whether the object contains buried ice beneath its dark outer layer. If subsurface ice exists, even a small amount of heating from the sun could eventually trigger weak outgassing activity. Such activity might be extremely subtle. Instead of producing a bright comet tail, the object might release only faint traces of gas that can be detected only by sensitive spectrometers. Detecting such emissions would be a major breakthrough. It would prove that even heavily irradiated interstellar objects can still contain volatile materials beneath their surfaces. That would help scientists understand how long icy bodies can survive in the harsh conditions between stars. At the same time, another powerful telescope is preparing to join the search. The Vera Rubin Observatory, located in Chile, is expected to begin full operations soon. Its enormous digital camera will repeatedly scan the entire southern sky with unprecedented sensitivity. Rubin's legacy survey of space and time will capture massive amounts of data every night. That means the observatory will likely track 3I Atlas continuously as it moves across the sky. The advantage of this system is long-term monitoring. Even when the object grows faint, Rubin's powerful imaging system may still detect it. This will allow astronomers to follow the object's path for years rather than months. Long-term tracking could reveal subtle gravitational influences as the object passes near giant planets like Jupiter. These interactions may slightly alter its trajectory. By measuring those tiny changes, scientists can calculate the object's mass more accurately. Mass estimates could reveal whether the nucleus is mostly ice, rock, or a mixture of both. Meanwhile, researchers are also exploring another fascinating possibility: tracing the object's origin. Every interstellar object enters the solar system from a particular direction in space. By studying that incoming direction and velocity, astronomers can estimate which region of the Milky Way the object may have come from. This process is extremely difficult because the galaxy contains billions of stars, each exerting gravitational forces that slowly change trajectories over time. But advanced computer simulations sometimes allow scientists to narrow down potential regions of origin. Early models suggest that 3I Atlas may have traveled through several dense star-forming regions before reaching our solar system. These regions are places where new planets are still forming. During the early stages of planetary formation, giant planets frequently scatter smaller objects outward. Many of those fragments escape entirely, becoming interstellar travelers. 3I Atlas could be one of those ancient fragments, a leftover piece from a planetary system that formed around another star long before our own sun was even born. And that is what makes this object so scientifically valuable. It is not just a comet passing through our sky. It is a messenger from another star system, a fragment of cosmic history that has traveled across the galaxy for millions of years before finally arriving here. And with each new observation scheduled for 2026, 2027, and beyond, astronomers are slowly uncovering more details about the mysterious nucleus that the James Webb Space Telescope has just begun to reveal. As more data started coming in, the global astronomy community began to treat 3I Atlas as one of the most important deep space discoveries of the decade. Not because it was dangerous, not because it was heading toward Earth, but because objects like this are incredibly rare opportunities to study the building blocks of other star systems. Every time a new set of measurements arrives, it adds another layer to the puzzle. And the puzzle surrounding the nucleus of 3I Atlas is becoming more fascinating with every observation. Researchers at NASA's Jet Propulsion Laboratory have been refining the object's orbit using updated tracking data from observatories around the world. Each night, telescopes send new coordinates to the Minor Planet Center, where the trajectory is recalculated again and again with increasing precision. Those calculations now show that 3I Atlas entered our solar system from a direction far above the plane of the planets, That is unusual, but not impossible. Interstellar objects can arrive from any direction in the galaxy because they are not bound to the gravitational disk where most planetary systems orbit. What matters more is the speed. And the speed of 3I Atlas confirms beyond doubt that it came from outside the solar system. Its incoming velocity is far higher than any comet that originated within our own system. Even the distant Oort cloud cannot produce objects moving this fast relative to the Sunday. That is why scientists are confident in its classification as an interstellar object. But the most intriguing question remains the one raised by the James Webb Space Telescope. What exactly is inside the nucleus? Early infrared scans suggested that the surface is darker than typical comet material. That alone was surprising. But when astronomers compared the spectral signals to known comet compositions, they realized the chemical fingerprints did not perfectly match the icy mixtures commonly seen in solar system comets. Some wavelengths hinted at carbon-rich compounds that may have formed under intense radiation. Others suggested a surface that has been altered by extremely long exposure to cosmic rays. Interstellar space is not empty. It is filled with energetic particles traveling at enormous speeds. Over millions of years, these particles can gradually change the chemistry of exposed materials. Laboratory experiments have shown that ice mixtures, bombarded by radiation, can produce complex organic compounds that absorb large amounts of light. Scientists refer to these radiation products as tholins. These materials are extremely dark and can form thick crusts on the surface of icy bodies. Similar compounds have been detected on Pluto, on distant Kuiper Belt objects, and even on the moon Titan around Saturn. If the surface of 3I Atlas is covered by a thick layer of such material, it could explain the unusual infrared signature detected by the James Webb Space Telescope. But that still leaves an important mystery. If the surface is sealed beneath a radiation-hardened crust, what lies underneath? Some astronomers suspect there may still be layers of ice buried below that dark outer shell. If that is true, the interior of the object could still contain frozen gases such as water, carbon dioxide, methane, or ammonia. These compounds are extremely common in the outer regions of planetary systems. But confirming their presence will require even more precise observations. That is why several major observation campaigns are already scheduled for the coming years. Astronomers are particularly excited about the viewing geometry expected during 2026 and 2027. During this period, the position of 3I Atlas relative to Earth and the Sun will allow longer observation windows. This means telescopes can capture higher quality data. The European Southern Observatory's very large telescope is expected to play a major role during those campaigns. Its advanced spectrographs can analyze faint light signals from distant objects with remarkable precision. At the same time, researchers at the Keck Observatory in Hawaii are preparing additional observation sessions to measure the object's rotation and brightness changes. Rotation is an important clue. When astronomers measure how the brightness of an object fluctuates over time, they can estimate how fast it spins and what shape it might have. Early measurements suggest that 3I Atlas may rotate slowly, but the data is still incomplete. If the rotation period can be determined accurately, scientists may eventually construct a rough three-dimensional model of the nucleus that would reveal whether the object is elongated, flattened, or irregular. Such information could tell astronomers how the object formed long ago in its original star system. Meanwhile, the James Webb Space Telescope may attempt additional infrared scans during future observation windows. Webb's instruments are sensitive enough to detect even faint traces of heat escaping from the object's surface. By mapping temperature differences across the nucleus, scientists can learn how quickly the object absorbs and releases solar energy. This type of measurement can reveal whether the surface is rocky, dusty, or icy beneath its outer layer. If buried ice begins to warm as the object moves closer to the sun, Webb may even detect faint gas emissions that were previously hidden. That would provide the first clear evidence of volatile materials trapped inside the nucleus. And that discovery would be extremely important, because it would confirm that interstellar objects can preserve ancient ice for millions of years while traveling between stars. In other words, these objects could act as frozen time capsules, fragments of distant planetary systems preserved in deep space. But perhaps the most exciting development is the possibility that 3I Atlas could remain observable for longer than previous interstellar visitors. When Oumuamua was discovered in 2017, it was already moving away from the sun rapidly. Scientists had only a short time to observe it before it became too faint. 3I Atlas appears to have arrived at a much better moment. With modern telescopes and improved detection systems, astronomers may be able to follow its journey across the sky for several years. This extended observation timeline means more data, more measurements, and potentially more discoveries. Because the deeper scientists look at the nucleus of 3I Atlas, the more they realize that this strange visitor from another star system may be carrying information about planetary formation processes happening across the Milky Way galaxy. As the months pass, the scientific attention surrounding 3I Atlas continues to grow. What began as a faint moving point of light in the outer solar system has now become one of the most discussed deep space discoveries among astronomers preparing for the next wave of observations. The reason is simple. The object is moving into a position that will allow the most powerful telescopes on Earth and in orbit to study it in ways that were not possible during its first detection. According to updated trajectory models calculated by specialists at NASA's Jet Propulsion Laboratory, several critical observation windows are expected between late 2026 and mid-2027. These future dates are already being marked across astronomy observation schedules because the geometry between Earth, the Sun, and 3I Atlas will improve dramatically during that period. When an object moves away from the intense glare of the Sun, telescopes can capture much clearer data. Longer exposures become possible, allowing astronomers to collect faint spectral fingerprints that reveal the chemistry of the object's surface. This is where the James Webb Space Telescope may once again play a major role. Webb's infrared instruments are designed to detect heat signatures from extremely distant objects. Even a small amount of thermal radiation can reveal how sunlight interacts with the surface of a comet or asteroid. During the upcoming observation events expected in late 2026, Webb could perform deeper scans of the nucleus to determine whether the dark surface seen earlier is hiding more complex structures beneath. Scientists are particularly interested in detecting temperature variations across the object's surface. If different regions of the nucleus warm and cool at different rates, that could indicate the presence of multiple materials. Rock, ice, and organic compounds all absorb and release heat differently. Mapping those thermal patterns can provide clues about the object's internal composition. At the same time, ground-based observatories will continue collecting optical and spectral data. The European Southern Observatory's Very Large Telescope is expected to conduct one of the most detailed spectroscopic campaigns ever performed on an interstellar object. The VLT's instruments can split incoming light into thousands of wavelengths, revealing tiny chemical fingerprints that may otherwise remain invisible. Meanwhile, the Keck Observatory in Hawaii will focus on another important measurement: rotation. By tracking subtle changes in brightness as the object spins, astronomers can determine how fast the nucleus rotates and whether its shape is elongated or irregular. These brightness curves are incredibly useful. Even without seeing the object directly, scientists can estimate its geometry from how it reflects sunlight over time. Early light curve data from 3I Atlas suggests that the object may rotate slowly compared with many known comets. If this slow rotation is confirmed during future observation campaigns in 2026 and 2027, it could mean the nucleus is unusually stable. That possibility has already sparked discussions among researchers at the Harvard-Smithsonian Center for Astrophysics. Some scientists believe the object may have formed in the outer region of another star system where collisions between icy bodies were less violent. In such environments, fragments may remain relatively intact when they are eventually ejected into interstellar space. But there is another possibility. Some researchers think the object may have experienced intense radiation exposure during its journey between stars, gradually forming a hardened outer crust. If that crust sealed the surface, it might prevent gases trapped inside the nucleus from escaping easily. This would explain why the James Webb Space Telescope detected such faint signs of activity. Typical comets begin releasing gas as they approach the sunday. That gas forms the glowing coma and tail that make comets so recognizable in the night sky. But 3I Atlas has shown little evidence of such activity so far. Instead, it behaves more like a silent traveler, drifting through the solar system with a surface that absorbs much of the sunlight hitting it. If future Webb observations detect buried ice beneath that crust, it could reveal something remarkable. It would mean that objects drifting through interstellar space can preserve frozen materials for millions of years while traveling between stars. In other words, 3I Atlas could be carrying ancient material from a planetary system that existed long before the sun formed. That possibility is why astronomers are planning long-term monitoring of the object. One of the most important instruments expected to contribute to this effort is the Vera Rubin Observatory in Chile. The Rubin Observatory is preparing to begin its massive legacy survey of space and time, a project that will repeatedly scan the entire southern sky with an enormous digital camera. Once the survey begins full operations, the telescope will capture thousands of images of the night sky every night. This continuous monitoring could allow astronomers to track 3I Atlas even as it moves farther away from the sunday. Long-term tracking is extremely valuable. It allows scientists to measure subtle changes in the object's path caused by gravitational interactions with planets like Jupiter and Saturn. These tiny deviations in trajectory can reveal the object's mass. Mass estimates are critical for understanding what the nucleus is made of. A mostly icy body will have a different density compared with a rocky fragment or metallic object. Determining the density of 3I Atlas could finally settle the debate about whether it behaves more like a comet or an asteroid. At the same time, astronomers are working on another challenge: tracing the object's origin. Every interstellar visitor enters our solar system from a specific direction in space. By studying that incoming direction and velocity, scientists can estimate where in the Milky Way the object may have formed. This process requires enormous computational simulations. Researchers model how stars move through the galaxy and how gravitational forces alter the paths of wandering objects over millions of years. Early simulations suggest that 3I Atlas may have traveled through regions of the galaxy where star formation is still active today. These regions are filled with young planetary systems, where giant planets often scatter smaller bodies outward. During the chaotic early stages of planet formation, enormous numbers of icy fragments can be thrown into interstellar space. Some of those fragments may wander the galaxy for billions of years before encountering another star system. That means the nucleus of 3I Atlas could be incredibly ancient. It might have formed before Earth even existed. And if that is true, the object drifting through our solar system right now may be carrying clues about planetary formation processes that happened in another part of the Milky Way long before our sun was born. That is what makes the upcoming observation events in 2026, 2027, and the years beyond so exciting for astronomers. Because each new observation could reveal more about the structure of this mysterious interstellar traveler. And the deeper scientists look into the nucleus, first scanned by the James Webb Space Telescope, the more it begins to look like one of the most important cosmic visitors humanity has ever had the chance to study. As the tracking of 3I Atlas continues, the conversation among astronomers has slowly shifted from simple discovery to something far more interesting. At first, the goal was only to confirm that the object was truly interstellar. But now researchers are asking deeper questions about how common objects like this might be across the galaxy. For a long time, scientists believed that interstellar visitors would be extremely rare. The detection of Oumuamua in 2017 changed that idea. Then Comet Borisov appeared in 2019. Now, with 3I Atlas entering the solar system, many astronomers believe we may just be starting to notice a much larger population of wandering cosmic debris. New sky surveys are dramatically increasing the chances of spotting these travelers. Projects like ATLAS, Pan-STARRS, and upcoming deep sky monitoring from the Vera Rubin Observatory are scanning the heavens constantly. Every night, huge portions of the sky are photographed again and again. Computers analyze the images and flag anything that moves against the background of distant stars. Because of these improvements, discoveries that once happened only once in a decade may soon become far more frequent. In fact, Some scientists predict that within the next 5 to 10 years, we could be detecting multiple interstellar objects every year. That possibility is one reason why the current investigation of 3I Atlas is so important. Each new object teaches scientists something about the environments where planets form. The chemical makeup of the nucleus, the surface texture, the rotation speed, and even the object's shape all contain clues about the conditions in the system where it originated. Researchers working with data from the Harvard Smithsonian Center for Astrophysics are particularly interested in the object's spectral signature. Spectroscopy allows scientists to identify molecules based on how they absorb or emit light. When light from the sun reflects off the surface of an object, tiny fingerprints appear in the spectrum. Those fingerprints can reveal whether the surface contains water, ice, carbon dioxide, methane, ammonia, or more complex organic compounds. Early readings from the James Webb Space Telescope hinted that the surface of 3I Atlas may contain radiation-processed materials that formed during its journey through interstellar space. But those results are still preliminary. That is why astronomers are eagerly waiting for the next major observation window expected toward the end of 2026. During this period, the object will move into a position where the viewing angle from Earth becomes much more favorable. With less interference from solar glare, telescopes will be able to collect much longer exposures. Longer exposures mean clearer spectral readings. This upcoming event is already being discussed across astronomy conferences and observation planning groups. Some researchers believe the data collected during that window could provide the clearest picture yet of the nucleus that the James Webb Space Telescope first scanned. The European Southern Observatory's very large telescope is expected to conduct one of the deepest spectral studies during that period. Meanwhile, the Keck Observatory in Hawaii will continue measuring brightness changes in order to refine the object's rotation period. Rotation is one of the keys to understanding the object's structure. If the nucleus spins slowly and evenly, it may be relatively stable and solid, but if the brightness variations reveal irregular movement, it could indicate that the object has a highly unusual shape. Some scientists have even suggested that 3I Atlas could be a fragment broken off from a larger planetary body long ago. In young planetary systems, collisions between large objects are common. These violent impacts can send fragments flying out of their home system entirely. Those fragments then begin wandering through interstellar space. Over millions or billions of years, radiation from stars and cosmic particles slowly alters their surfaces. This is why many interstellar objects appear darker than typical comets found inside our solar system. Radiation processing can transform simple ice mixtures into complex organic materials that absorb light instead of reflecting it. If the surface of 3I Atlas has been shaped by this process, the dark crust detected by Webb might actually be protecting the interior. Beneath that surface, there could still be frozen gases that have remained trapped for millions of years. Detecting those gases would be an extraordinary discovery. If scientists observe even faint traces of water vapor, carbon dioxide, or methane escaping from the nucleus, it would confirm that interstellar objects can preserve volatile materials during their long journeys through the galaxy. That would have major implications for planetary science, because it would suggest that the building blocks of planets, and possibly even the ingredients for life, can survive interstellar travel. This idea is not new. Decades ago, astronomer Ronald Bracewell at Stanford proposed that material could move between star systems through natural cosmic processes. While his work mostly focused on the concept of interstellar communication probes, the underlying physics also applies to drifting objects like comets and asteroids. Fragments ejected from planetary systems could carry organic molecules across the galaxy. Some scientists believe this process may have helped spread complex chemistry between star systems over billions of years. Objects like 3I Atlas could be part of that story. They're not just frozen rocks drifting through space. They may be time capsules, pieces of ancient planetary systems traveling across the Milky Way. And right now, one of those fragments is passing through our solar system, while the most advanced telescopes ever built are watching it. Over the next few years, from the observation campaigns expected in late 2026 to extended tracking that may continue into 2027 and beyond, astronomers will continue studying this mysterious visitor. Each new set of data may reveal something unexpected, a hidden layer of ice, a strange rotation pattern, a chemical fingerprint never before detected in a comet nucleus. And the deeper scientists investigate the nucleus first scanned by the James Webb Space Telescope, the more it becomes clear that 3I Atlas may not just be another comet. It may be one of the most scientifically important interstellar visitors humanity has ever had the chance to observe. As the scientific community prepares for the next phase of observations, something interesting is beginning to happen behind the scenes. The discovery of 3I Atlas is no longer being treated as just another comet report. It is quickly turning into one of the most anticipated deep space investigations scheduled over the next few years. Astronomers now believe that the real story of this object may not unfold in a single observation. Instead, it will likely reveal its secrets slowly through a series of future observation events that stretch into late 2026, throughout 2027, and possibly even into 2028 as telescopes continue tracking the object while it exits the solar system. That extended timeline is incredibly important. In previous cases like Oumuamua, scientists had only a very short window to study the object before it became too faint to observe. By the time the Hubble Space Telescope and ground observatories focused on it, the visitor was already racing away from the sundae. But 3I Atlas appears to have arrived at a much better moment for modern astronomy. New survey systems now detect objects much earlier in their approach. That gives scientists more time to plan observation campaigns and coordinate telescope schedules across the world. Right now, researchers at NASA's Jet Propulsion Laboratory are continuously refining the object's orbit using new tracking data arriving almost daily from observatories. Each update improves the accuracy of predictions about where the object will appear in the sky months or even years from now. These predictions are critical for planning the next round of high-precision observations. One of the most important observation windows is expected during the final quarter of 2026. During this period, the position of 3I Atlas relative to Earth will create ideal viewing conditions for long exposure imaging. With the object moving farther away from the sun's glare, telescopes will be able to collect cleaner spectral signals. This means the chemical fingerprints of the nucleus could become much clearer. The European Southern Observatory's very large telescope is expected to play a major role during that campaign. The VLT's spectrographs are capable of detecting extremely faint molecular signatures, allowing scientists to identify compounds that would otherwise remain hidden. At the same time, astronomers at the Keck Observatory in Hawaii are planning a series of rotational monitoring sessions. Their goal is to measure the object's spin with greater precision than ever before. Understanding the rotation of 3I Atlas could unlock a major clue about its origin. If the object spins very slowly, it may indicate that it was once part of a larger body that broke apart during a collision. Fragments from such events often have irregular shapes and slow rotation speeds. But if the rotation turns out to be faster or chaotic, it could mean the object has experienced gravitational interactions during its long journey through the galaxy. These possibilities are exactly why astronomers are preparing such detailed observation schedules. But perhaps the most powerful tool in the investigation remains the James Webb Space Telescope. Webb's infrared instruments can detect tiny temperature differences across the surface of distant objects. By mapping those variations, scientists can determine how the surface absorbs sunlight and how quickly it releases heat. These thermal measurements may reveal whether the nucleus contains hidden layers beneath its dark outer shell. Earlier scans hinted that the surface may be covered by radiation processed materials formed during millions of years of exposure to cosmic rays. But what lies beneath that crust is still unknown. If buried ice exists inside the nucleus, even a small increase in solar heating could eventually trigger weak gas emissions. Detecting those emissions would be a historic moment. It would prove that interstellar objects can carry volatile materials across the galaxy for incredibly long periods of time. And that discovery could reshape how scientists think about planetary formation and chemical exchange between star systems. Meanwhile, another major telescope is preparing to join the investigation. The Vera Rubin Observatory in Chile is expected to begin its full sky survey soon. Once operational, the Rubin telescope will photograph the entire visible sky every few nights using one of the largest digital cameras ever built. This survey, known as the Legacy Survey of Space and Time, will generate enormous amounts of data. Because the telescope repeatedly scans the sky, it will be able to track moving objects with extraordinary precision. That means 3I Atlas could remain visible to Rubin's cameras even as it grows faint while leaving the solar system. This extended monitoring could continue well into the late 2020s. For astronomers, that is extremely valuable. Long-term tracking allows researchers to measure tiny changes in the object's trajectory caused by gravitational interactions with planets such as Jupiter and Saturn. Those small shifts in the orbit can reveal the object's mass. Mass estimates are essential for understanding the density of the nucleus. If the density is low, the object is likely composed mostly of ice. If it is higher, the nucleus may contain significant rocky material. Determining that composition would help scientists understand where the object formed. But the investigation goes even deeper than that. Astronomers are now running complex computer simulations to trace the object's path backward through the galaxy. By analyzing its incoming direction and velocity, researchers can estimate which regions of the Milky Way it may have traveled through before reaching our solar system. Early models suggest that 3I Atlas may have originated near a region of active star formation. These regions are filled with young planetary systems where giant planets frequently scatter debris into interstellar space. During the chaotic early stages of planet formation, countless fragments are ejected from their home systems. Most drift silently through the galaxy forever. But a few eventually encounter another star. One of those fragments may now be passing through our solar system. And if the predictions about the upcoming observation events in 2026, 2027, and beyond are correct, astronomers may soon uncover the true nature of the mysterious nucleus that the James Webb Space Telescope has already begun to reveal. Because with every new observation scheduled in the coming years, the story of 3I Atlas is moving closer to answering one of the most fascinating questions in modern astronomy. What exactly is this interstellar traveler carrying with it across the vast darkness between the stars? As astronomers continue monitoring the strange traveler moving through our solar system, one thing has become clear. The story of 3I Atlas is unfolding in real time. And every new observation is slowly revealing more about what this object truly is. Right now, observatories across the world are preparing for what many researchers are calling the next critical observation phase. According to updated projections released by orbital analysts working with NASA's Jet Propulsion Laboratory, the viewing geometry of 3I Atlas will improve dramatically as the object moves farther from the sun's glare. This improvement will begin gradually toward the end of 2026 and will continue through several key observation periods expected during 2027. Those dates are already appearing on the calendars of major astronomical observatories. When objects move into darker parts of the sky, telescopes can collect longer exposures. Longer exposures mean more photons reaching the detectors. More photons mean clearer spectral data. And clearer spectral data means scientists can finally identify the materials present on the surface of the nucleus. Researchers from the European Southern Observatory are planning a series of deep spectroscopic scans using the Very Large Telescope in Chile. The VLT's instruments can split incoming light into thousands of narrow wavelengths, allowing astronomers to detect even faint traces of molecules on the surface of distant objects. At the same time, astronomers working at the Keck Observatory in Hawaii will continue measuring the brightness variations of 3I Atlas as it rotates. These brightness fluctuations are extremely valuable. When an object rotates, different surfaces reflect sunlight toward Earth. By carefully measuring those changes over time, scientists can estimate the object's rotation period and even infer its shape. If the brightness swings are large, the nucleus may be elongated or irregular. If the brightness remains relatively stable, the object may be more spherical. Early data suggests that 3I Atlas may rotate slowly, but astronomers need more observations to confirm this. Slow rotation could indicate that the object has remained relatively stable during its long journey through interstellar space. It might also suggest that the nucleus is fairly large compared to the fragments that make up typical comet nuclei. Meanwhile, the James Webb Space Telescope is expected to conduct additional infrared observations during the upcoming observation windows. Webb's infrared detectors are sensitive enough to measure tiny temperature differences across the surface of distant objects. These thermal maps can reveal how sunlight interacts with the nucleus. If certain regions warm faster than others, it could mean that the surface is made of different materials. Rock, ice, and radiation process organic compounds all behave differently when exposed to sunlight. Mapping these differences may help scientists determine whether the object contains buried ice beneath its dark crust. That possibility is extremely exciting. Earlier observations suggested that the outer surface of 3I Atlas may have been hardened by millions of years of exposure to cosmic radiation. When objects drift through interstellar space, high-energy particles constantly bombard their surfaces. Over long periods of time, this radiation can transform simple ice mixtures into complex organic residues. These residues, often called tholins, are extremely dark and absorb most of the light that hits them. Tholins have been observed on several distant bodies in our solar system, including Pluto and some Kuiper Belt objects. If the surface of 3I Atlas is coated with similar materials, it could explain why the nucleus appears darker than most comets. But what lies beneath that crust remains one of the biggest mysteries. If frozen gases are still trapped inside the nucleus, future heating from the sun could eventually trigger subtle outgassing activity. Unlike typical comets, this activity might be extremely weak. Instead of producing a bright glowing tail, the object might release only faint traces of gas detectable only by sensitive spectrometers. Detecting those gases would be a major breakthrough. It would prove that interstellar objects can preserve volatile materials while traveling between stars for millions or even billions of years. Such a discovery would have enormous implications for planetary science, because it would suggest that the building blocks of planets and complex chemistry can survive long journeys through interstellar space. Meanwhile, another telescope is preparing to join the investigation. The Vera Rubin Observatory in Chile is expected to begin its full sky survey soon. Once operational, the Rubin telescope will scan the entire visible sky every few nights using one of the largest digital cameras ever built. This massive project, known as the Legacy Survey of Space and Time, will generate enormous amounts of astronomical data. Because Rubin repeatedly scans the same areas of the sky, it will be able to track faint moving objects over long periods. This means astronomers may be able to follow 3I Atlas for years as it gradually leaves the solar system. Long-term monitoring is incredibly valuable. By tracking the object over extended periods, scientists can detect tiny gravitational interactions with planets like Jupiter and Saturn. These interactions can slightly alter the object's trajectory. By measuring those changes precisely, researchers can estimate the object's mass. Mass estimates help determine density, and density reveals whether the nucleus is mostly ice, rock, or some combination of both. At the same time, scientists are working on one of the most challenging tasks in modern astronomy, tracing the object's origin. Every interstellar visitor enters our solar system from a particular direction in the galaxy. By studying the incoming velocity and direction of 3I Atlas, astronomers can run simulations that trace its possible path through the Milky Way. This is incredibly complex work. The galaxy contains billions of stars, each exerting gravitational forces that slowly change the trajectories of wandering objects over millions of years. Even small interactions can alter a path dramatically over long periods. But advanced computer models are now capable of simulating these gravitational influences. Early simulations suggest that 3I Atlas may have passed through several regions of active star formation before reaching our solar system. These regions are filled with young planetary systems where giant planets often scatter debris into interstellar space. During the chaotic early stages of planet formation, huge numbers of icy fragments can be ejected into the galaxy. Most of these fragments will never encounter another star system, but occasionally one drifts close enough to another star to be captured temporarily by its gravity. That may be exactly what happened here. A fragment from a distant planetary system wandering through the Milky Way for millions of years has now entered our solar system at a time when humanity has the most advanced telescopes ever built watching the sky. And as the next major observation campaigns approach in late 2026, early 2027, and beyond, scientists believe that the true nature of the mysterious nucleus first scanned by the James Webb Space Telescope may finally begin to reveal itself. As the investigation moves deeper, astronomers are beginning to realize that the timeline of this discovery may stretch much farther than anyone expected at the beginning. When the first data from the James Webb Space Telescope hinted that the nucleus of 3I Atlas might be unusual, scientists initially thought the mystery would unfold quickly. But instead, the object has become the focus of a long-term international observation campaign that could continue well into the late 2020s. One reason for this is the unique timing of the discovery. Unlike earlier interstellar visitors, such as Oumuamua, which was already leaving the solar system when it was detected, 3I Atlas was identified much earlier in its journey. That early detection gives astronomers more time to observe it under different lighting conditions as it moves through space. Orbital specialists working at NASA's Jet Propulsion Laboratory have now calculated a series of predicted observation opportunities that will occur throughout late 2026 through several major observation windows during 2027, and possibly extending into early 2028 as the object continues moving outward. Each of these dates is extremely important for astronomers. When an object like 3I, Atlas, moves through different regions of the sky, the angle between Earth, the Sun, and the object changes. This affects how much sunlight reflects off the nucleus and how easily telescopes can observe it without interference from solar glare. The upcoming observation season, expected toward the end of 2026, is already attracting enormous attention among research teams. During this period, the object will appear in darker regions of the sky, allowing telescopes to capture longer exposures and higher resolution spectral data. Longer exposures mean that faint chemical fingerprints can be detected more clearly. Scientists at the European Southern Observatory are preparing to use the Very Large Telescope for one of the deepest spectral scans of an interstellar object ever attempted. The VLT's instruments can detect extremely faint absorption lines that reveal the presence of molecules, such as water, ice, carbon dioxide, methane, and complex organic compounds. At the same time, the Keck Observatory in Hawaii is preparing a series of rotational monitoring campaigns. Rotation may sound like a simple measurement, but it is one of the most powerful tools astronomers have for studying distant objects. As an object rotates, different parts of its surface reflect sunlight toward Earth. By tracking these changes in brightness, scientists can calculate the rotation period and estimate the object's shape. If 3I Atlas has an elongated structure or an irregular surface, the brightness variations could reveal that. This technique was used during the investigation of Oumuamua when astronomers discovered that its brightness changed dramatically as it rotated. Those observations suggested the object might be extremely elongated compared with typical asteroids. Now scientists are wondering if 3I Atlas could reveal another unusual structure. Early brightness curves hint that the nucleus may rotate slowly and unevenly, but the data is still incomplete. More precise measurements expected during the 2026 and 2027 observation windows may finally provide a clearer answer. Meanwhile, the James Webb Space Telescope remains one of the most powerful tools available for studying the object. Webb's infrared detectors allow astronomers to measure heat emissions from extremely distant objects. These thermal signals reveal how sunlight is absorbed and released by the surface. Mapping temperature differences across the nucleus can show whether certain areas contain ice while others are made of rock or organic materials. Earlier scans hinted that the surface of 3I Atlas may be covered by a thick radiation processed crust formed during its long journey between stars. If that crust exists, it may be protecting the interior from solar heating. But if the object contains buried ice beneath that crust, future observations may eventually detect faint gas emissions as the nucleus warms slightly while passing through the solar system. Even the smallest trace of water vapor or carbon dioxide would be an extraordinary discovery. It would prove that interstellar objects can preserve volatile materials for millions of years while traveling through the cold vacuum between stars. That discovery alone would provide important clues about how planetary systems exchange material across the galaxy. But there's another exciting development happening at the same time. The Vera Rubin Observatory in Chile is preparing to begin full operations. This telescope will conduct one of the most ambitious sky surveys ever attempted. Its enormous digital camera will scan the entire visible sky repeatedly over a 10-year period. This project, known as the Legacy Survey of Space and Time, will produce a continuous record of moving objects in the night sky. Because Rubin repeatedly images the same regions of space, it will be able to track faint objects like 3I Atlas even as they move farther away from the sunday. This long-term monitoring could continue well into the late 2020s. That extended observation period is extremely valuable. By tracking the object for years instead of months, astronomers can detect tiny gravitational influences from planets such as Jupiter and Saturn. These influences slightly alter the object's path through space. Measuring these changes allows scientists to calculate the object's mass. Mass measurements then reveal density. And density is the key to understanding whether the nucleus is mostly ice, rock, or some combination of both. Meanwhile, another group of researchers is working on one of the most ambitious parts of the investigation: tracing the object's origin through the Milky Way galaxy. By analyzing the incoming velocity and direction of 3I Atlas, scientists can run simulations that estimate where the object may have formed before beginning its journey through interstellar space. This process is extremely complex because the galaxy contains billions of stars whose gravitational fields slowly alter the paths of wandering objects over millions of years. But advanced computer models are becoming more powerful every year. Some early simulations suggest that 3I Atlas may have passed through several dense star-forming regions during its journey across the galaxy. These regions are filled with young planetary systems where giant planets frequently eject debris into interstellar space. During the chaotic early stages of planetary formation, enormous numbers of icy fragments are thrown out of their home systems. Most will drift through the galaxy forever, but a small number eventually pass near another star. And one of those ancient fragments may now be passing through our solar system at exactly the moment when humanity has the most powerful space telescopes ever built watching the sky. As the next major observation campaigns approach in late 2026, through 2027 and into the years beyond, scientists believe the mystery surrounding the nucleus first scanned by the James Webb Space Telescope may finally begin to unfold in ways that no one expected when the object was first discovered. For months, the data kept arriving slowly, one observation at a time, from telescopes spread across Earth and from the instruments orbiting far beyond it. Each new measurement was small on its own, a spectrum here, a brightness curve there, a faint thermal signal captured by the James Webb Space Telescope. None of these pieces looked dramatic at first, but when scientists placed them together, the picture that began to form was far more interesting than anyone expected when 3I Atlas was first detected. The deeper astronomers looked into the nucleus, the clearer one thing became. This object was not behaving exactly like the comets we know from our own solar system. The infrared scans from the James Webb Space Telescope showed a surface that absorbed enormous amounts of light. Observations from the Keck Observatory revealed rotation patterns suggesting an irregular structure. Spectral fingerprints analyzed by teams working with the Harvard Smithsonian Center for Astrophysics hinted at radiation process materials formed during extremely long exposure to cosmic rays. In other words, the object had spent a very long time traveling through deep space before arriving here. And then came the moment that quietly changed how scientists talked about the discovery. When updated thermal maps from Webb were compared with spectral observations from the European Southern Observatory's Very Large Telescope, researchers realized something surprising. Beneath the dark outer surface, there were hints that the nucleus might still contain volatile compounds trapped deep inside. If those compounds truly exist beneath the radiation-hardened crust, it means something extraordinary. It means the object drifting through our solar system may have preserved frozen materials for millions or even billions of years while traveling between stars. That realization changes the way scientists think about interstellar visitors. Instead of being simple rocks drifting through space, they may be ancient time capsules carrying chemical records from distant planetary systems. The nucleus of 3I Atlas could be a fragment from a world that formed around another star long before our sun was born. A fragment that survived violent planetary formation, escaped the gravity of its home system, and then wandered through the Milky Way for ages before crossing our path. And right now, for the first time in human history, the most powerful telescopes ever built are watching such a visitor in real time. Future observation campaigns scheduled through late 2026 and across 2027 may reveal even more. As the viewing geometry improves and instruments collect deeper spectral data, astronomers may finally confirm the true composition of the mysterious nucleus first scanned by the James Webb Space Telescope. But even before those answers arrive, the discovery of 3I Atlas has already done something important. It has shown us that our solar system is not isolated. The galaxy is full of wandering fragments from other planetary systems, and every once in a while, one of them drifts close enough for us to study. Each one carries a story from another part of the Milky Way. And with each new interstellar visitor we detect, we get a small glimpse into the processes shaping planets around distant stars. So the next time you look up at the night sky, remember that somewhere out there, drifting silently through the darkness, ancient fragments from other worlds are traveling between the stars. And sometimes, just sometimes, one of them passes close enough for humanity to see it. If you want to keep following discoveries like this and see what the James Webb Space Telescope reveals next, make sure you subscribe and like the video. It helps this channel continue bringing you real space discoveries and deep space mysteries as they unfold.